this function right here, and we're asked to find the number of zeros in the annulus given by the mod of z being between 1 and 3. Okay? Now, first I want to remark that we never ever have to worry about if f would be, would attain a 0 on the boundary. Okay? Because we're going to find a function L and B such that B of z is strictly greater than L of z on each of the boundaries here, and that will lead us to conclude that will lead us by Rouche's theorem to say that L and B plus L have the same number of zeros on the boundary, and because of this strict inequality, it's not possible for this function right here, which is going to be f, to have a 0. Okay? Now, the question is, what do I choose my B? What do I choose for my B? Let's take mod z less than 3, because that seems the most obvious one. So B of z, I'm going to take to be, well, if I look here, this guy right here is going to be the dominant term. Right? At least I expect it to be the dominant term. Okay? And if that's really the case, if B of z, the mod of B of z is strictly greater than the rest, then that will tell me that all of the zeros of f, well, okay, so this is not exactly necessarily, well, it'll tell me, okay, never mind. Anyway, I'm going to take B of z to be this, okay? Now, the absolute value of B of z is 2 times 3 to the power of 6, okay, on the boundary here of the bigger disk. Let's look at L of z, and L of z will have to be then minus 5 z squared plus e to the minus 3 sine of z. Absolute value, let's be very generous, use the triangle inequality. And now, it's clear what to do here. It's going to be 45, right? Because this is equal to, okay, so we know that z is equal to, the mod z is equal to 3 on the boundary, so this is 3 squared times 5, so that's 45. Okay, now I've got to bound this from above. You might be tempted to say that this is less than or equal to 1, but that's only true for, if I had a strictly real variable here. Okay, remember that sign is unbounded on the complex plane. Okay, so instead, there's this, well, I know intuitively at least that on the imaginary axis, this is where the function becomes unbounded because it starts behaving like, well, it starts being exactly the hyperbolic sine or the hyperbolic cosine. Okay, so actually you can form this inequality, right? So if we let z equal x plus iy, you can form this estimate, this sandwich right here of inequalities. Okay, now just to prove this, it's actually pretty straightforward. So sine of z is e to the iz plus e to the minus iz over 2i. Take the absolute value. This gives me a 2 on the bottom. This is a minus, sorry. Now, for this part, I can do less than or equal to, and be very generous and use the triangle inequality. Okay, now I use the fact that if I've got e to the something which is purely imaginary, that is going to have an absolute value of 1. Okay, well, e to the iz is e to the I into x plus iy, which is e to the minus y times e to the ix. E to the minus iz is e to the plus y, e to the minus ix. Yes, that's certainly true. So now if I take the absolute value, this is just 1. This is positive real value, so there you go. And so I can replace this literally with e to the minus y, and I can replace this with e to the y. Okay? But then this is nothing but cosh of y. Okay, if I want the lower bound, I use the reverse triangle inequality. Okay, and so replace by e to the minus iy, that's e to the y, over 2, can put an I here, put the whole thing in modulus, and that's thus, actually sorry, sorry, no, my bad, that, and then, yeah, that's 2, and then this whole thing, well, that's just shine, absolute value of shine of y. Okay, so anyway, I'll leave it at that. So I can bound this above by 45 plus e to the minus 3 cosh of y, and so that is less than or equal to, well, on the unit on this ball right here, the most that the imaginary value can be is y is equal to 3. So that's e to the minus 3 times cosh of 3. So e to the 3 plus e to the minus 3 over 2. And you can check that this is very comfortably below, well, less than or equal to 46. Okay, and this is quite comfortably less than 2 times 3 to the power of 6, which is the absolute value of b of z. So the absolute value of L of z is strictly less than the absolute value of b of z on this boundary. Okay, now that means that f has got 6 zeros inside this disk. Now let's look at the unit disk. Okay, so let me write this out again. Now, you might think a little bit and say, okay, I can take b of z to be, you might say, okay, let me take L of z to be this guy, right? Because it's e to the minus 3, that's rather small, and sine of z, I can basically bound this, I could definitely bound this above by something that's going to be small enough, right? And that works perfectly fine. Then if you think a little bit more, right, and you think about the number of zeros of this, right, you expect there to be 2 zeros, right? And in fact, this has only 2 solutions on the unit disk. So actually, because I'm anticipating that there is going to be 2 zeros, instead, I can be even a little bit more bold and take this guy to be b of z instead. Okay? And in fact, I could maybe have sort of thought that I can take this to be b of z because the coefficient of this guy is rather large, right? And we're on the unit disk. So roughly speaking, obviously this is not a surefire way, but sort of intuitively, you might start off thinking, okay, maybe this is a good choice for b of z. So let's actually do the test on the boundary. So the absolute value of b of z is equal to 5. So we've got to show that L of z is less than 5. Okay? So L of z has to be 2z squared plus e to the minus 3 sine z. Okay? So, well, I can use the reverse triangle inequality, right? Yeah, I think that's fine. So, reverse triangle inequality. Oh, my bad. We're trying to estimate L of z from above, right? We're trying to show that L of z in absolute value is strictly less than b of z. So we can use the triangle inequality, right? And again, we can use the, well, this is equal to 1 on the boundary, right? That's the point. Because we're on the unit disk, this is not going to really dominate anymore. Now, this is less than or equal to 2 plus e to the minus 3 times cosh of y, right, the imaginary part of z. And this can be at most This can be at most 1. Okay, and then this is equal to 2 plus e to the minus 3 into e to the 1 plus 1 over e, all of that divided by 2. Okay, and what we've really got to check, make sure for ourselves that this is less than 3, right? But that's sort of obvious, right? If I expand this out, this is 1 over e squared, and then 1 over e to the 4. This is less than 1, this is less than 1. This entire thing is just going to be less than 1, therefore. So this is certainly, in fact, less than 3, right? And that's strictly less than 5, so we're good. Okay, and so f has got 2 zeros. So f has got 2 zeros here, and it's got 5 zeros on the entire thing. Now you might ask, okay, what if there are some zeros on the boundary that we missed? Because obviously Rouche's theorem only tells you the number of zeros on the interior. Well, because of the fact that L of z is strictly less than B of z, and f is equal to B plus L, there can be no zeros on the boundary. That's not possible. And so that tells us that there are 3 zeros on here, and that's the answer.